applied to change that state. Newton's first law of motion. Galileo, the ideas he gave, actually Aristotle started all, and then Galileo gave the flaw in Aristotle and he corrected the concept. After that, new mechanics was developed, and this was accomplished single-handedly by Isaac Newton, one of the greatest scientists of all times. Newton started, or he took Galileo's ideas as the base, and then he laid the foundation of mechanics in terms of 3 laws, which we know by his name. So Galileo's law of inertia was the starting point, which was he formulated in terms of first law of motion. Every body continued to be in the state of rest in a straight line, or uniform motion in a straight line, unless it is compelled by some other or external force not to do so. So the state of rest or uniform linear motion, they both imply zero acceleration. Acceleration is zero while the body is at rest or in uniform velocity. How can we express it again? If the net external force on a body is zero, its acceleration has to be zero. We'll see later that in the second law of motion, F is equal to ma. We'll learn about this. So F equal to m into a. If the acceleration is zero, force is zero. So acceleration can be non-zero only if there is a net external force on the body, right? This can only be non-zero when you have some force here. The net external force in the body, if it is zero, as we said, because of this discussion, the body is either at rest or it is moving in uniform motion. A spaceship out in interstellar space, which is far from all other objects and with all its rockets turned off, it has no net external force acting on it, that is zero force acting on it. So the acceleration, according to the first law, it has to be zero. If it is in motion, it has to move with uniform velocity. So where does this force comes? That the object is, say, accelerated or unaccelerated. You can say if it is unaccelerated, that means it is in rest or uniform linear motion. What we can infer is that by first law, that the net external force on an object must be zero. But gravity is everywhere. If you take any terrestrial phenomena, every object experiences some gravitational force which is due to the earth. The objects in motion, they generally experience the friction, the viscous drag, so many things. So the net force which is acting is very important. We'll learn about that, how those forces cancel up, how those forces they get added up. Just consider a book which is lying on the table. Now there is a force of gravitation which is acting downward, which is W, weight. There is a normal force opposite to it, and this R is self-adjusting force. These forces are opposite to each other. That is why, what is happening? This book is at rest. So what we can conclude by the first law, that the magnitude of R has to be equal to W, because this is at rest. So all the net force which is acting on this body should be zero. So there is only two forces which we can conceive here. One is weight, one is some reaction force. So R has to be equal to W, and they cancels out. And since they cancel out, the body remains at rest. But is this reasoning correct? The correct discussion should be, since the book is observed to be at rest, there is no net external force on it, or the net external force on it must be 0, 0. So R minus W equal to 0. This should be the proper reasoning. That means the force, this R, has to be equal and opposite to this weight. Let us take one more example, that is a motion of a car which is starting from rest. It is starting with initial velocity 0. Now it is picking up speed and then moving on a straight road, and now it has uniform speed. When the car was at rest, that is, it was stationary, there was no net force, but during pickup, you push the acceleration is being pushed by you. Okay, and there would be some external force. That is why it has accelerated, and there is no external force here because the acceleration is coming from the engine. So the acceleration of the car cannot be accounted for by any internal force. But it is true. It is surprising, but it is true. We need to understand only the conceivable external force along the road is the friction force which is acting between the tires and the road. This is the friction force which is being acted upon. So when the car is moving with constant velocity, there will be no net external force. And the inertia, body will continue in rest, body will continue in moving the state. When we are standing stationary in the, say, stationary bus, and the driver starts the bus suddenly, what will happen? We will get thrown backward with a jerk. Why? Because our feet, see, we are sitting like this. Our feet are in touch with the floor. So if there were no friction, we would remain where we are, while the floor of the bus would simply slip forward under our feet, and the back of the bus would hit us. But what happens? Fortunately, there is some friction between our feet and the floor. So if the start is very fast, if it is not too sudden, you can say the acceleration is moderate. The friction force would be enough to accelerate our feet along this bus. But our body is not a rigid body, it's flexible, it is deformable. So it allows some relative displacement between different parts. We can move our parts. So which means that while our feet go with the bus, the rest of the body remain where it is due to inertia. So relative to the bus, therefore we are thrown backward, and as soon as this happens, our muscular force, body forces, they start acting upon, and they play to move the body along the bus. And this same scenario will happen when the bus will suddenly stop. If it suddenly stops, our feet stop due to the friction, which does not allow relative motion between the feet and the floor of the bus. But the rest of the body continues to move forward due to inertia. That is why we are thrown forward. But we have restoring muscle forces. This will come into play and bring our body to rest. Let us take a question. An astronaut accidentally gets separated out of his small spaceship accelerating in interstellar space at a constant rate of 100 meters per second square. What is the acceleration of the astronaut the instant after he is outside the spaceship? we have presumed that there are no nearby stars that are going to exert gravitational forces on him. And since it is being said that there are no nearby stars to exert gravitational force on him, and this small spaceship exert very little or negligible gravitational force or pull, the net force acting on the astronaut when he comes out of the spaceship is zero. And we know by the first law of motion, the acceleration has to be zero.